We're going to look at calculating the area of a polar region. When we calculate the area of a polar region, instead of using rectangles as our basic shape, we want to use sectors of a circle. And the area of a sector of a circle where the angle here is theta is equal to A equals 1/2 theta r squared. And when we're looking at a polar region, r equals f of theta, that's the radius, and then it's going to go from some alpha to some beta. And you can see that you could think of that as divided into a bunch of subsectors. And so if you think of infinitely many subsectors, the limit as n approaches infinity of the amount of subsectors here, subintervals on alpha to beta. That means that area is equal to 1/2 times the integral from alpha to beta of f of theta squared d theta, or just r squared of theta, whichever way you want to think of it. And we do think of that beta minus alpha being between 0 and 2 pi. So I've gone ahead and graphed this polar region r equals 6 sine theta. It's centered at 0, 3, and it's got a diameter of 6. And mostly what I'm looking for from this graph is what the interval for alpha and beta is. So for this, in order to get this entire graph, all of these points, I need to go from alpha equals 0 to beta equals pi. Now remember to be careful with polar coordinates, because the area, the quadrant where the points lie is not necessarily the angle where it comes from, so you do want to put some test points in there and just make sure your interval is what you expect it to be. So for this one, A equals 1/2 times the integral from alpha to beta of r squared d theta. So that's going to be 1/2 times the integral from 0 to pi of 6 sine of theta squared d theta. And we're going to square both the 6 and the sine, so that'll be 36 sine squared of theta d theta. And I am going to bring this 36 out front, so that'll be 36 over 2, which is 18, times the integral from 0 to pi of sine squared theta d theta. And now I'm going to apply an identity, because the only way to take the integral of sine squared of theta is to convert it to 1 minus cosine of 2 theta over 2. So I'm just applying that identity. 1 minus cosine of 2 theta over 2 d theta. And so now I'm going to split that into two integrals. I'm going to have 18 times the integral from 0 to pi of 1/2 d theta minus 18, and let's just go ahead and bring the 1/2 out. The integral from 0 to pi of cosine of 2 theta d theta. So this one is easy. This is 18 over 2 is 9 theta from 0 to pi. With the other integral, you're going to need to do a u substitution where u equals 2 theta. So du is 2 d theta. So I need a 2 here and a 1/2 here. So that's going to be minus 9 over 2. The integral of cosine of u du is sine of u. So sine of 2 theta. And that's going to go from theta equals 0 to pi. So now we just evaluate, and we'll have 9 pi minus 0 minus 9/2 times sine of 2 pi minus sine of 2 times 0. And of course we know that this is 0 and this is 0, so I really just get 9 pi. Units squared is my answer, because it's units of area. Okay, so we are looking at, we're trying to find the area of one petal of r equals sine of 2 theta. And r equals sine of 2 theta is a rose curve. N equals 2, so you double that because it's even to get that there's 4 petals. There's a 1 out front here, so they're each of length 1. And because we are looking at a sine rose curve, the symmetry is going to be on the y-axis, so your graph looks like this. And if I just want the area of one petal, I'm going to go from 0 to pi over 2. Now if you needed 2 petals, you could double that, 3 petals, you could triple that, whatever, because each petal is the same. So the area, of course, is 1/2 times the integral from 0 to pi over 2, or from alpha to beta, technically, if we're looking at the formula, of r squared d theta. So that'll be 1/2 times the integral from 0 to pi over 2 of sine of 2 theta squared d theta. Now we just looked at an example that used the rule that said sine squared of u equals 1 minus cosine of 2u over 2. In this case, we're looking at sine squared of 2 theta, so that's going to be 1 minus cosine of 4 theta over 2, because we double that 2 theta and get the 4 theta. So I've got 1/2 times the integral from 0 to pi over 2 of 1 minus cosine of 4 theta over 2 d theta. And just to handle things a little bit better than we did last time, let's go ahead and bring the 1/2 out and get 1/4 times the integral from 0 to pi over 2 of 1 minus cosine of 4 theta d theta. And splitting it up, that'll be 1/4 times the integral from 0 to pi over 2 of 1 d theta minus 1/4 times the integral from 0 to pi over 2 of cosine of 4 theta d theta. So we'll have 1/4 theta from 0 to pi over 2 minus 1/4. Now with this one, we'll let u equal 4 theta. So du will be 4 d theta, which means I need a 4 and another 1/4 out here. So that's really 1/16, and that'll be sine of 4 theta from 0 to pi over 2. So I get 1/4 times pi over 2 minus 0 minus 1/16 times 4 times pi over 2 is 2 pi minus sine of 0. So of course this again is 0 and 0. So my answer then is pi over 8 units squared. For this one, we want to find the area of the interior of r equals 1 minus sine of theta. R equals 1 minus sine of theta forms this cardioid right here, and we're looking at the entire thing, so we are going to be looking from 0 to 2 pi. So the area, which is 1/2 times the integral from alpha to beta of r squared d theta, is going to be 1/2 times the integral from 0 to 2 pi of 1 minus sine of theta squared d theta. So with something like this, we want to go ahead and FOIL that out. So square the first gives me 1, double the product gives me minus 2 times 1 times sine of theta, and square the last gives me plus sine squared of theta, and that's all d theta. So now I'm going to split it, and I'm going to make 3 integrals out of it. So we'll have 1/2 times the integral from 0 to 2 pi of 1 d theta. 1/2 times negative 2 gives me minus 1 times the integral from 0 to 2 pi of sine of theta. And then we'd have plus 1/2 times the integral from 0 to 2 pi of sine squared of theta, d theta. And we do need a d theta on all of these, so be careful with your notation. Okay, so from there, I have, with the first one, 1/2 theta from 0 to 2 pi. We don't have to do a whole lot of work there. Minus the integral of sine is negative cosine of theta from 0 to 2 pi, so that becomes a plus. And then with the last one, we're going to have to apply that same trig identity. You're going to see that one come up quite a bit. You may also have to use the cosine version of it, so just make sure you're aware of that. But that is 1 minus cosine of 2 theta over 2 d theta. So this gives me 1/2 times 2 pi minus 0 plus cosine of 2 pi minus cosine of 0 plus, now we're going to have the 1/2 times 1/2 is 1/4 times the integral of d theta. And then here we'll have minus 1/4 times the integral from 0 to 2 pi of cosine of 2 theta d theta. And that's just bringing that 1/2 out and then turning it into the cosine of 2 pi. So of course, sorry, 2 theta. So of course we need a 2 to accommodate that u equals 2 theta. So I'll multiply by 1/2. Hopefully that's becoming familiar. We've done that enough times in this video. So this is pi. This is our 1 minus 1, which is 0. This will be 1/4 times 2 pi minus 0, minus 1/8 times the sine of 2 theta from 0 to 2 pi. So we have pi plus pi over 2 minus 1/8 times sine of 4 pi minus sine of 0. And this is 0 and this is 0. So I really just have pi plus pi over 2, which is 3 pi over 2. And that'll be units squared. You can also do arc length for polar curves. If we let f be a function whose derivative is continuous on an interval from alpha to beta, the length of the graph of r equals f of theta from theta equals alpha to theta equals beta is found as the integral from alpha to beta of the square root of r squared plus r prime squared d theta. So for this example, we've got r equals 4 sine of theta and the interval is from 0 to pi. So r equals 4 sine of theta. And dr over d theta, or r prime, is 4 cosine of theta. So my arc length would be the integral from 0 to pi, that's my interval here, of the square root of 4 sine of theta squared plus 4 cosine of theta squared d theta. And then you just follow wherever the calculus and the trig take you and integrate this thing. So here I would have the integral from 0 to pi of the square root of 16 sine squared theta plus 16 cosine squared theta d theta. And if I break out the 16, that's just sine squared of theta plus cosine squared of theta, which we know this is 1. So really we have the integral of the square root of 16, or 4 d theta. And that's super easy. That's 4 theta from 0 to pi. So we get 4 pi units. Now this one is arc length, so this is not units squared. It's just units of length. And that would be my answer. There's also a formula for the area of a surface of revolution in polar coordinates, and this varies depending on whether you're revolving around the polar axis or the line theta equals pi over 2. The only real difference is the sine here and the cosine here. So you're always going to have r, and you're always going to have r squared plus r prime squared. But if you're revolving around the polar axis, you'll have a sine of theta, and if you're revolving around the line theta equals pi over 2, you'll have a cosine of theta. So for this example, we're looking around the polar axis, so we know we're going to be looking at this formula. So my s is going to be 2 pi times the integral from alpha to beta of r sine theta times the square root of r squared plus dr over d theta squared d theta. And my alpha is 0, my beta is pi over 2, and my r is 6 cosine of theta. So the only other piece of information I need is dr over d theta, which is going to be negative 6 sine of theta, the derivative of that guy right there. So this will be 2 pi times the integral from 0 to pi over 2 of 6 cosine of theta sine of theta times the square root of 6 cosine of theta squared plus negative 6 sine of theta squared d theta. Now before you look at this and go, oh no, what am I going to do? This is actually pretty good. We're in a good position here because I can go ahead and, let's see, I can bring the 6 out if I want, or I can wait a minute. It doesn't really matter. But I'm going to write sine of theta cosine theta. I like that order better. And here, if we factor out the 6 squared, we would have 36, and we would have cosine squared of theta plus sine squared of theta because the negative gets squared. And we know that this is just 1. So the whole square root is 6. So really I have 2 pi times 6 times the integral from 0 to pi over 2 of sine of theta cosine of theta d theta. And hopefully you recognize this integral from 8.3, I think it was. We let u be sine of theta, and du would be cosine of theta d theta. So this is our u, and this is our du, so this is u squared over 2. So I have 2 times 6, which is 72 pi, and my integral is going to be sine squared of theta over 2, that's the u squared over 2, and it's going to go from 0 to pi over 2. So that gives me 36 pi times sine of pi over 2 squared minus sine of 0 squared. And this is 1 and this is 0. So we get 36 pi. This is area, so that'll be units squared. For this last problem, it says we're going to revolve the curve of r equals 4 sine of theta around the line theta equals pi over 2. So for this one, we are on case 2. And the only difference is going to be we're going to have a cosine instead of a sine. So let's see how that changes things. So I've got r equals 4 sine of theta. I know that s, and this is a capital S, is equal to 2 pi times the integral from 0 to pi over 2 of r, which is 4 sine theta, and then cosine theta, because of the thing that we're revolving around, the square root of r squared, which is 4 sine theta, plus dr over d theta, the derivative of that, which is 4 cosine of theta squared d theta. So this is going to be very similar. If we have our 4 sine of theta, cosine of theta, we have the square root of 16 times sine squared of theta plus cosine squared of theta d theta. This goes away. 4 times 4 is 16, so we end up with 32 pi times the integral from 0 to pi over 2 of sine of theta cosine of theta d theta. And this is again our u, and this is our du, so we have 32 pi times sine squared of theta over 2 from 0 to pi over 2. So I end up with 16 pi times sine squared of pi over 2 minus sine squared of 0. So this is 16 pi times 1 squared minus 0 squared, or 16 pi units squared. Now, if you don't end up with this situation, the sine of u, cosine of u, if you end up with a cosine squared of theta or a sine squared of theta, you can look back at the previous examples in this video and see how you deal with that type of integral. But once you set it up, you just kind of have to follow whatever the integration gives you. They're not all going to be exactly the same, but these are some of the patterns that you tend to see.